All right, can you all hear me okay?
Yeah.
Okay, good. All right, so let me make a couple of adjustments here. So let's get started. Our last lecture. And this one lecture is on the whole chapter. This will be probably the least rigorous lecture I give this semester, just because of the nature of the material. So some of the things I'll probably do might not be satisfying to folks, but the issue is the math can get pretty hairy if you start getting rigorous. So a lot of hand waving here. Reminder, Unit 5 exam is on Thursday. I mean, we will have office hours tomorrow from 4:30 to 6 so I can answer your questions. Okay? So don't forget the office hours tomorrow. I did email you the a practice exam for Unit 5 so you can take a look at it. Okay? And I got it, hopefully I didn't make any mistake. It was like 1:30 when I finished it, so in the morning. So if you notice anything strange, just let me know right away. Okay. Don't forget the lab kits are due on the 25th. And make sure you see the instructions on the box. Okay. The box itself, in fact, on the box cover, because I saw Tyler yesterday said it says on the box to read the instructions. Okay. So read the instructions on how to turn it in. Just make sure your name is on it. Okay, and if you want to, you can email me a picture of you dropping it off. Okay, you can email me a picture of you dropping off your lab kit, putting it into one of the boxes. There will be boxes outside of Sewell Hall, and you'll have a box for our class. So just dump it in the box. It'll say for physics labs. Okay, but get it done by the 25th between Friday and the end of next week. I have to be grading your exam and your 2 labs and your lab kit. So it's actually 3 labs, but that's really not much grading to that. So I have a bunch of stuff to get done for you. Okay, because the grades are due not this Friday, but the following Friday. Okay, that's why I can't have anything turned in late. I can't extend anything because I gotta get going and grade things.
Is there a drop-off in Nevada County, at the Nevada County campus?
Oh, that's a good question. Did you pick yours up at the bookstore in Nevada County?
Mine got shipped.
Yours got shipped.
House. Yeah.
Okay. Check the instructions. In fact, I just got an email from Tyler. I think. Hold on a second. Let me check the email from Tyler. Yeah, it says you can mail it back to Sierra College.
Oh, okay.
Okay. And I don't know. I'm hoping there's instructions on there about mailing it back. If not, I'll send you I'll send you the email that Tyler sent me. Okay, just let me know. Because I haven't seen the instructions.
All right.
Okay. Other questions? Or concerns?
I had a question on the lab.
Sure.
So we were talking about it in the Discord, but I just wanted to make sure. So when it says under the data, like right there where it says like R equals and then C equals and L equals, is that R just the resistance of the resistor, or is that everything in the circuit?
Well, yeah. So normally when we do the lab on ground, the R is just the resistance of the resistor. And then when the student starts doing the analysis and they realize, oh, I have to include the resistance of everything else. So there will be a place later on, usually in the lab, where you have to say that, oh, I have to include the resistance of everything. So yeah, you can just put the resistance of the resistor there. Is that okay?
Okay. And then in the analysis later, you find like the total R, right?
Yes.
Okay.
Like when you calculate your Q, you need a total R. Otherwise, it's going to be way off. And that's where you can say, I have to include everything, because otherwise it's going to be way off. Is that okay, Vincent?
Yeah, that's good. Thank you.
So there's some questions in the chat. So yeah, the last exam cannot be dropped. You have to take the last exam. It's not your final, but it's your last exam. Okay, I only dropped the first 4. Okay, it specifically says that in the syllabus. Okay, yeah, I think the return box though is, it says 9 to 4:30 because somebody picks everything up by 4:30. I'm sure that if you came at 6 and you drop something off there, it'd probably be fine. Just take if you can't come between 9 and 4:30, okay, just drop it off later. Just mean that nobody can pick it up after, nobody's going to be there to pick up after 4:30. Okay. Well, does it say that calculate it, or
It's for the part of the lab where it is asking for just the values that it says L and C should be, the inductor and the capacitor. It just has a spot for the value and then plus or minus. But as far as I know, they don't have uncertainty.
well, for L, I said, yeah, for L you can't measure. So L, I said to use just 10 plus or minus 1. But for C, since you can measure, because I showed a video of how to make the measurement of the capacitor, you can measure it and then use the manual to tell you how well you know that number.
Okay, cool,
Okay.
thank you.
And I didn't change the instructions in the lab, or I didn't have chance to change it because I don't always know what I'm going to get for a multimeter. So this multimeter allows you to measure capacitance. It's possible that I would have gotten one that doesn't allow me to measure capacitance. It just depends on what's available when we order it. But now we have a nice collection of them, so we should be okay for a long time. But yeah, it's better to measure it. You will find, I'm guessing you will find that the capacitance that you get from your table when you take the average value will be less than what you measured with the meter. And that's because the signal generator has a capacitor at the output. And its effect will be less pronounced as the frequency increases. Okay.
And for the uncertainty, it is just standard deviation, right?
You mean from the table?
Yeah.
Yeah. I mean, standard deviation divided by the square root of the number of measurements.
Yeah.
Yeah.
Okay.
Anything else?
And just to make sure, the X sub L and X sub C was the voltage divided by current, right, for the corresponding element?
Yeah, the RMS, the voltage across the inductor divided by the current. Yeah.
And then we get L and C from that.
Correct, yes.
Okay.
And do it in Excel.
Yeah, it is in Excel.
Okay, because otherwise it's painful. Okay, last chapter that we're doing is on really electromagnetic waves. It's really a combination of the course essentially, okay? Because we've studied these equations already. These are called Maxwell's equations, and they describe essentially everything in this course. Really, it describes everything about fields in this course. If we want to add something involving forces, I'm not going to use Coulomb's law, but I'm going to talk about the Lorentz force. Okay? So these are the main equations. So, and I should say this, these are the equations, these equations are not written in their most useful form. They're more useful when they're written in the differential form. Okay? So, when Maxwell came up with the idea of the displacement current, he had this set of equations, and then he started, to manipulate them. And under various conditions. And I'm not going to go through and talk about the manipulation of the equations. By the way, before I forget, I spelled this wrong. If you want a little bit more details as to what I'm saying today, there is a fantastic 3-volume textbook on introductory physics that was made by Richard Feynman in the 60s. It's based on his lectures. And this is the website. And our lecture is based on volume 2, chapter 20. And he goes in more details about this chapter, except that, you have to realize that he goes into Calc 3 into that. He does do Calc 3 in there. Okay, so if you want to add some Calc 3 into this lecture, go watch these, not watch, but read this chapter in the book online. Okay, it's available for free, so you can just look at it. So, these are the fundamentals for E&M. And like I said earlier, if you incorporate Maxwell's equations plus the Lorentz force law, you have everything summarized in this course. Okay? Now, if you manipulate the equations, which I'm not going to do here, okay, Maxwell's equations predict electromagnetic waves that travel through space. And I kind of alluded to that because when we wrote down the following equations, oops. I alluded to the fact that in some cases there has to be a wave traveling through space in order for us to be able to explain some situations. For example, you have a solenoid and you have a time varying current, and then you have a loop around the solenoid on the outside. There'll be an EMF induced in this loop. There'll be a current in that loop. And so how does the information get from the solenoid to that wire? Well, there must mean that there's got to be some sort of wave traveling through space. So this equation plus this one are important because this says that a time-varying electric field generates a magnetic field. This says that a time-varying magnetic field essentially generates an electric field. Okay. So, oops. Let me go slower. If we have a situation where we solve Maxwell's equations and we end up getting an electromagnetic wave that travels in the y direction. So suppose solutions to wave equation and what I mean by that is if you take those four equations and put in some sort of conditions and solve them, you get something called a wave equation. Suppose that the solution to the wave equation says that a wave travels in the y direction. Okay, suppose that we comes up with that solution. Okay, if that's the case, you'll see that the dot product, and I use y hat in the notes for some reason, the dot product of y hat and the direction of the electromagnetic field is 0. The dot product of y hat, the direction of travel of the wave, and the magnetic field is 0. It says that the electric field and the magnetic field are perpendicular to each other. Okay? And they're perpendicular to the direction of travel of the wave. Furthermore, y hat cross E, forgot to write this one down, is equal to C times B. So E is perpendicular to B, and the direction of travel of the wave is perpendicular to both E and B. So in fact, the direction of travel of the wave, the electric field, and the magnetic field, they form a right-handed coordinate system. So you can draw a right-handed coordinate system. Okay, this is the direction of travel of the wave. Here's E, the direction of E. Here's the direction of B. These form a right-handed coordinate system.
Hey, Professor.
Yeah.
Does a time-varying magnetic field create a time-varying electric field, or is the electric field created uniform?
Be careful. Uniform and constant mean different things. But yeah, time-varying magnetic field will create, unless it's linearly dependent on time.
Right. Well, the reason I bring it up is because if a magnetic field generates a time-varying electric field, then isn't there like a perturbative effect there where it like then generates its own magnetic field?
Yes.
Okay.
Yeah, when you talk about electromagnetic waves traveling through space. So what they do is they work together when we talk about waves traveling through space. If you're thinking about an electric field that's a magnetic field that varies linearly with time, it will not be, you will not get a solution. You will not get a solution to the wave equation for the case where B is depends linearly on time. You won't get one.
Okay. Thank you.
Okay. Because the wave equation depends on a second order derivative.
Right. Yeah.
Yeah. So it won't satisfy the wave equation. So does everyone understand what it means by the fact that these three form a right-handed coordinate system? Okay.
So coming out of the page is just where you, like, that's your Y.
this would be my y. I guess I should have done it differently, but it's easier for me to
Oh
draw.
no, that's fine. I just wanted to.
Yeah. So
clarify.
if I curl E into B, my thumb points in the direction of travel of the wave. So it obeys a right-hand rule. Okay. The direction of travel of wave obeys a right-hand rule. E cross B is in the direction of travel of the wave. And that's important because we're going to define a vector a little bit later on that relates the direction of travel of the wave with energy. Now you can use these equations to derive all the laws of optics. Now it's interesting that before Maxwell's equations, there were folks who actually developed models to understand various effects or various phenomena that are observed in optics. For example, interference, diffraction. There were various models that were used to describe them, but really, they really come from Maxwell's equations. Maxwell's equations gives you a fundamental basis to derive all the laws of optics. The solution of Maxwell's equations also predicted that waves travel at the speed of light. It's 3 times 10 to the 8th meters per second. Okay. And this was verified by Hertz. And in fact, when he solved his equations, he was able to show that light waves refract, light waves interfere, etc. A lot of his predictions were verified by Heinrich Hertz later on. The equations also predict that waves are produced from accelerated charges. So if you have a charge that's accelerating, the accelerating charge will emit electromagnetic radiation. So let's talk about the simplest solution to the wave equation. It's called a plane wave solution. It assumes that the waves, the source of the electromagnetic waves, are far away. Generally, what you do is you set I equals 0 and Q equals 0. That's what that means. So you set up Maxwell's equation, you set I equals 0, you set your Q equals 0, and then you manipulate them and solve them. Okay, and you get something called the wave equation. And one of the solutions to the wave equation is called a plane wave solution. Really what it is you have a source of waves that's far away, a periodically oscillating source that's really far away from the point of observation. Okay? And so I just want to talk about some of the characteristics of the periodic solution, the plane wave solution. We're assuming this, again, the source is really far away. So I'm going to draw what would be representative of an electromagnetic wave when you're really far away from the source. And I'm going to show it to you a little bit later where it comes from, but the electromagnetic wave will look kind of like this. Doesn't matter whether I use cosine or sine. And I'm just going to make up a direction of oscillation. So what this means is if I wanted to plot this, the oscillations are in the z direction. So this is the z direction. Let me make this y. And this is the x direction. So the wave is traveling this way. The oscillations are this way. And this is due to some periodic source, some oscillating charge that's really far away from us. And when it's really far away from us, then the approximate solution essentially is this. Or if you set Q equals 0 and I equals 0 in Maxwell's equation, you solve it, you'll actually will get this solution. So notice that this thing repeats itself. The distance through which it repeats itself is called a wavelength. Is denoted by the Greek letter lambda. The time it takes for the wave to repeat itself is called a period.
Professor?
Yes.
Should the horizontal axis be y or is it x?
Oh, yeah. Thank you.
Okay.
So if the wave travels this distance in the time period t, then the speed of the wave, c, is lambda over t. Of course, what we physicists look at is not the period, but the number of cycles per second. Which is 1 over the period, which is called a frequency. And so the speed of light then is written as lambda times frequency. And the lambda is characteristic of the wave. It's a characteristic of the wave. It's a characteristic of the source, basically, that's producing that wave. Now, the electric field, this is the electric field, I didn't label it. The magnetic field will be oscillating in phase with the electric field, but perpendicular to the plane of the electric field. So if the electric field is oscillating this way, the magnetic field is oscillating in the x direction. Okay, so electric field is oscillating in the x direction, if this is in the y direction. And then the direction of travel, I'm sorry, yeah. So the wave is doing the magnetic field is doing this, okay? Okay? Actually, I really messed it up. I'm sorry, I messed this up big time. Because I drew my picture wrong. Hold on a second. Yeah, we're okay. We're fine. Never mind. It's just that the magnetic field oscillates in the x direction. I had it okay. I got myself mixed up. Okay. So another quantity that we define is called the wave number.
Just to clarify, that E with the vector on top of it, that's the electric field?
The U, which U?
Oh, the E.
This one?
At the top.
Oh, that one? Yeah.
Oh, okay. And then the EM is the electromagnetic wave?
Is the amplitude, so it's this distance.
Oh, okay.
Okay. It's the maximum value. So K is 2 pi over lambda. That's called the wave number. Okay. And if we take this C and we multiply numerator and denominator by 2 pi, it gives us C is omega over K. So that's another relationship. So these are some of the relationships, and what you can see here is there's a lot of just simple equations in this chapter. Okay. So this gives you some of the characteristics of a wave. This is a plane wave. Again, we're assuming that the source is far away from the point of observation.
Professor?
Yes.
So omega here for this situation, is it something if we were depicting it in the form of a circle? Like, I can see F here, but how would I see omega here? Like on the picture that you have on the board.
How would you picture omega?
Yeah. Like usually we have like a circle or something.
Yeah, it's really reflective of the phase of your function. And I guess the question is, why do I define an omega, right? I mean, that's the question to ask, is why do I define an omega? Because really what I want to do is, when you take a cosine of something or raise something to a power, this part called the argument, what must be true about it? What must be true about it? What's in here? What if you take omega times t? What are the units?
It has to be an angle.
Yeah, well, yeah. I mean, it has to be dimensionless, right?
Mm-hmm.
Right. And so we introduce omega just to make this dimensionless. I mean, the reason why we introduced one of the reasons why we introduced a k, there's another reason, but is to make this whole thing dimensionless. If you solve the wave equation, okay, you'll see that you get something that doesn't depend on this. We write it this way because it looks dimensionless. So this makes sense now. You're taking the cosine of something that's dimensionless. I know radians is, or degrees is not really a real unit in physics. Right, a radian is a distance divided by distance, the units cancel. Does that make sense?
Yeah.
Yeah, so yeah, we don't really talk, it's not, that omega is not related to an angular velocity or like an, anything that you would cover maybe like in, when you take 215, you talk about oscillatory motion.
Mm-hmm.
Okay. So, and I do this backwards, but if you solve Maxwell's equations, or if you manipulate Maxwell's equations for the case that I equals 0 and Q equals 0, no source, you get two sets of equations, one for the electric field and one for the magnetic field. And the solutions can look like this. They don't have to look like this, but they can look like this. And so you get two sets of equations. And I know I'm doing a lot of hand waving. There's second order differential equations. But if you had physics 215, you've seen some form of this equation for waves on a string. And mu naught times epsilon naught is 1 over the speed of light squared. So there's a set for E and a set for B. And this, what I wrote down is a one-dimensional version of it. But think about this. There should be an equation for this for the X component electric field, the Y component electric field, and Z component electric field. There should be three sets of these for the electric field, and then 3 sets for the magnetic field. Okay, we usually in a class like this, we only show this one. We try to keep the math simple, and then when you because the idea is to learn the concepts. You take a more advanced course, then you can look at it in 3D. Okay. Is it the gradient vector? It's not the gradient vector squared. I guess it's you ask a Calc 3 question.
Honestly, if it's not, we should probably just keep going.
Okay.
I'll ask you
Well,
now.
it's the divergence of the gradient vector.
Gotcha. But yeah, anyway, if I have any more questions, I'll just ask you at a different point. It's not worth it.
Okay.
Wait, is that on the first term, what you wrote on the left board? Is that an Y on the bottom?
These are all X's, sorry.
Oh, okay. And then
But there's a set for Y, there's a set for Z.
and then the one to the very right, is that, oh, that's C squared on the bottom?
C squared, yeah, because
Oh, okay.
1 over C squared is mu naught times epsilon naught. Now, in general, if you solve this particular equation, and I'm not worried right now about the vector nature of the total field. In general, the electric field, and let's just write the magnitude like this, which I screwed up in my notes. But should look more like this, is some function of x plus or minus c times t. Magnetic field is the same thing. I guess I can do this. It's okay for me to do that, I guess. Both E and B have this form. The plus sign means a wave traveling to left. A minus sign is a wave traveling to the right. Assuming that way is positive and that way is negative. That's counterintuitive, isn't it? Are you okay with that? Does that bother you that the minus sign tells you is a wave traveling to the right?
Yeah, it's completely opposite of what you would think.
And Kai, you're right. It does sound like trig. I mean, suppose, those of you who took, I know not everyone takes pre-calc, but there's at some point when you take math, you do about transformation equations in of graphs. You know, you switch to a one coordinate system to this coordinate, and you rewrite, let's say, a parabola. Okay, and you do transformations. When you go to the right, everything's always minus. But think about it this way. Suppose I have a wave that's traveling to the right. And let's assume that the wave looks like this, just for simplicity. Okay, it's a big pulse, which is basically some linear combination of omegas or whatever. So let's say that you have a wave traveling that way. Let's say you're moving with the wave. So the wave is going at that speed and you're moving in that direction. That thing's going to look the same to you all the time, right? Yeah, let's say you're moving at the speed of light. But we can talk about it in terms of a wave on a string too. It doesn't matter. Okay? Let's say you're moving with the wave. If you don't like moving at the speed of light, we can talk about a wave on a string. And if you're moving together, you're just looking at the shape the whole time, which is some function of x. I'm going to call it x prime. So you're standing here, you're moving with the wave, and the wave is f of x prime. Now somebody over here just sitting here and says, well, x prime is x minus ct.
Is it just coincidence that these look exactly like the transformations from special relativity?
Well, I mean, we're not doing special relativity, but Galilean relativity.
Yeah, sorry.
Yeah, that's right. I mean, it's just a Galilean transformation. That wave is moving relative to us. So now, according to me, this person, a coordinate in this person's frame is written this way. When you put this into the equation, you get a wave traveling to the right, and there's the minus sign. And I know if you've had, at some point in math before calculus, you've done these kind of transformation problems, especially if you had pre-calc. Okay. Because I remember my son in high school, when he took pre-calc, he had to do these kind of transformation problems. Okay, so yeah, the minus is wave traveling to the right, a plus is a wave traveling to the left, assuming right's positive, left's negative. Okay? So, one set of solutions will have the cosine and sine functions. Okay? This is the general solution, but the simplest solution that I can talk about really is the kind where E looks like this. And we say, well, what happened to the C there? Oh, I can factor out the K. If I factor out the K, and this is a C. And when you put this when you take this guy and stick it into this equation, the K will cancel out. The E and the B that you see in the slide just represent the amplitude of the wave.
Professor?
Yeah.
So, I don't know whether this is like correct or not, but the equation for E and B both have X. So should one be Y or Z something, or both are X and it is fine? Or are we talking about different waves?
Oh, you talking about oh, you mean for these two?
Yeah.
Well, this is the direction of travel of the wave, right?
Mm-hmm.
They're going to be in the same direction. It's the direction of oscillation which varies.
And how did we know the direction of oscillation from that equation?
I never specified it.
Okay.
Yeah, I never specified it. That's why that's why I wanted to put absolute values on everything. I wanted to make it a magnitude because I didn't really specify. In fact, here I just wrote E with the arrow over it.
Mm-hmm.
So I wasn't specific at all. A lot of times in physics, when they want to make it general, they'll do this. That could mean anything.
Yeah.
Okay, and I didn't want to do that because people say, "What is E?" So I did it non-specifically. The vector is subsumed into that, so it's somewhere in there.
Yeah.
Okay.
Wait, so X shows the direction of the wave? I thought it was
X is the direction of travel of the wave. It's not the direction of the oscillation.
Okay.
All right. And if you go back to 2 graphs back, okay, this part of the motion is not this. This is the direction of travel. It's not the direction of oscillation. If you talk about a wave on a string, right? If you take a string and you jiggle it up and down and let the wave travel, right? Let's say the wave travels away from me. That's the direction of travel of the wave. That's what's in here. But the jiggling up and down is something else.
And then that when you wrote EM times cosine K, is the cosine is it cosine of K times
X
plus or minus CT?
You talking about here?
No, to the right.
Yeah, this whole thing in parentheses.
So inside the cosine, it's so K is the only thing inside the cosine?
That whole thing is inside the cosine.
Oh, okay.
Okay. The whole thing's dimensionless. Okay. All right, let me go back. And I know talking about this in a very hand-wavy way a lot of times is not very satisfying, but we're limited here. So in terms of, you need to know a lot more math to be able to actually do these. In fact, solving Maxwell's equations in general are hard. So I asked this question already, what about the phase difference between electric field and magnetic field? It is true that the oscillations are in different planes. The oscillations of the waves, the magnetic field and electric field, they're 90 degrees apart, but the peaks occur at the same time, the valleys occur at the same time. So the electric field and magnetic field, they are in phase, just remember that, but their plane of oscillations are 90 degrees apart. So, if you can see in the slide, maybe I'll make this bigger because it looks kind of tiny. You see those two. Do those two represent electromagnetic waves? But notice I say electromagnetic because electric fields and magnetic fields really essentially have come from the same source, right? The magnetic field is a relativistic manifestation of the electric field. How do I know those are solutions to the Maxwell's equations? How would I prove it?
Just take their second derivatives with respect to x and time and plug them in.
Yeah, that's right. So if I ask you to prove whether or not those two, I used to do this as a worksheet, but kind of late to ask this for you guys to do this, but all you got to do is plug the E equation in here and see if the left side equals the right side. And of course, if I change these E's to B's, then I would take the second equation, plug it into Maxwell's equation and see what we get. And it turns out that these are solutions to Maxwell's equation, and I've plotted their profiles in the picture. Okay, that's a graph of their profiles at different times. The kind of waves that you get really depends on the problem. I mean, the conditions that you set up. Now, I will say this, there's these plus or minus terms. In general, and if you've had 215, the same idea. Right? If you had 215, you talk about waves on a string. The only difference is the wave on a string is the solution is a scalar, not a vector. In general, I'll just write E. Solution has that kind of form. Some function where this is a plus and some function where that's a minus. That's the general solution. If you do not have any boundaries anywhere, then only one of these exists. If you have boundaries, if a wave bounces off of something, then both of these have to exist in your solution. Both of them will solve this equation. Okay. So if you have both of them, that means there's some boundary somewhere. The wave is bouncing off of something. But, and that's true with, waves on a string. If you've had 215 already. Okay. But if you have only one of the two, then you have a wave that has no boundaries. It just travels forever and ever. Which is, granted, an idealized situation. But that's what we encounter in this course. Okay, we generally just encounter idealized situations. So, we have these waves. Let's talk about the wavelengths, lambda. Okay? By the way, I need to pause for a minute. I need to check on something, okay? I will be back in a minute. I'm sorry, I need to go check on something. All right, sorry about that interruption. Okay, so let's talk about the characteristic of a wave in terms of lambda. You can have, really, we have a whole spectrum of electromagnetic waves, and they range from really various sources. Let me show you the figure. Let me blow up the figure because it's kind of small. Electromagnetic waves can have very long wavelengths. Now, we're not talking about gravitational waves here, okay? Because we're not talking about sources, the sources from electromagnetic fields. And you can see that the wavelengths can be longer than 1,000 meters if you look at the top. And just to give you an idea, it shows you, some radio waves are the size of a soccer field or a house. Okay. And then the waves, as you go to the right, the wavelength gets smaller, the frequency gets higher. You look at the microwave range. The microwave range goes from about 0.1 meters to about 10 to the minus 4 meters, that ballpark. What are the source of microwaves? Where do you see microwaves being generated? Well, you'll see them in an atom. Okay? I'm sorry, not an atom, a molecule. A large molecule. Transitions in molecules will generate microwaves. And then the next range goes from around 10 to the minus 3 to about 10 to the minus 6 meters. That's the infrared regime. And atoms and molecules, transitions in atoms and molecules will produce infrared radiation. And look at how tiny the visible spectrum is compared to all the other ones. The visible spectrum ranges and as a physics major, or actually as a student who's had this class, you should know that the visible spectrum goes from 400 nanometers to 700 nanometers. This is violet. And it's red. Okay. Especially if you also end up taking 215. This is something you need to know. That should be basic knowledge for you. Okay. What do you mean you can't see anything, Rataj? We can't see anything.
Like if you look at that range and our ability to see is just that tiny little bit.
Oh yeah, you're right. It's really tiny, right?
Yeah.
It's of interest to people like artists and other folks, but to us, to physicists, all the wavelengths are interesting. They have some sort of interest to us, right? And that little part is what's important to us because we use those wavelengths to see. Okay, it's a really small range, and we can convert this to frequencies because we know that V equals F lambda, or C is F lambda, and so F is C over lambda, and the frequencies are in the neighborhood of 10 to the 14th hertz. Okay, the visible spectrum is in the range of 10 to the 14th hertz. Okay, then you go to ultraviolet. And so now you start talking about ionizing radiation. So when you go into UV, the ultraviolet light can change the structure of an atom. It can sight the electrons in an atom. Invisible light can too, but more so with ultraviolet. And then you go to soft X-rays, hard X-rays, and then gamma rays. One of the things you should realize is that there is no definite boundary between one set of electromagnetic waves to the other. Okay, there's no definite boundaries. So how do you differentiate gamma rays from hard X-rays? The gamma rays, the source of gamma rays are nuclear decay. The source of hard X-rays are from accelerated particles. Okay, that's generally how we differentiate them, but there's no hard boundary between one part of the electromagnetic spectrum and another. And as you go higher in energy, go higher in, I went ahead of myself. You go higher in frequency, the energy of the wave increases. So you will learn when if you take 215, that waves can be described in terms of these massless particles called photons, and each photon has an energy of h times f, where h is Planck's constant, 6.63 times 10 to the minus 34 joule seconds as units of angular momentum. Okay, and so as you go smaller in frequency, smaller in wavelength, higher in frequency, the photons have more energy.
Does the fact that Planck's constant has units of angular momentum have anything to do with why it's called spin?
Why it's called spin? Well,
Yeah.
the idea of, that's fortuitous because Planck's constant came before the idea of spin.
I see.
Yeah, because Planck's constant came around 1895. The idea of spin came in the late 20s. But it's interesting that if you look at the angular momentum of an atom, that it's it's actually h over 2 pi times some number. Okay. So h over 2 pi, it's called h bar, is involved in the angular momentum of the atom. So how are electromagnetic waves produced? Well, there are really two sources of electromagnetic waves. One is when you have free charges accelerating, and another is when you have bound electrons making transitions in atoms, or you have transitions in molecules between various electronic states, rotational states, and vibrational states. You can also get transition within the nucleus of the atom, and that produces the gamma rays. So it's either transitions within a nucleus, within the atom, or within the molecule, or you have accelerated charges. Those are the only sources of electromagnetic waves. Here's a picture showing you an oscillating dipole. The black that you see, there's basically a charge that's oscillating up and down, and it's showing you the generation of the electric and magnetic fields. The red's the magnetic field, the blue is the electric fields as a result of the oscillation. And the energy is always carried perpendicular to the oscillating dipole. And one thing to remember, that electromagnetic waves act like particles because they carry energy, linear momentum, and angular momentum. Okay, here's another picture for a radiating dipole pattern. So very quickly then, I want to talk about the energy, the flow of energy. And again, like I'm saying, I'm being very hand-wavy today. I want to talk about the flow of energy as a result of electromagnetic waves. So I want to consider a wave penetrating that box. Its area is A, and its thickness is dx. So imagine an electromagnetic wave, electric field oscillating up and down, traveling in the x direction. And the magnetic field is also showing. Okay, the wave's traveling in the x direction at speed c. I want to look at the energy that goes through that volume. The volume is the area, A, times the thickness, dx. I want to look at the energy per unit area, per unit time. It's called the power. I want to look at the energy per unit area, per unit time. And then we're just going to define it as du dt divided by the area. Okay? So let me write that down. And I'm going to label it with the letter S. And again, I'm defining everything in not a very rigorous way, but it'll work for us. Okay, so we said the power per unit area. We define it as the magnitude. We'll call it S. We'll write it like that. I'm kind of foreshadowing. Okay. And by the way, this has units of watts per meter squared. And this is really, I'm going to write it this way. I'm going to say, well, S is 1 over the area times du over dt. But let's do an aside here. du is the energy density times dV. And this energy density is due to the electric field and the magnetic field. The electric and magnetic field carry the energy. When the electric field is 0, all the energy is magnetic. When the magnetic field is 0, all the energy is due to the electric field. Okay, just think of an oscillating field. And so this is going to be U sub E plus U sub B.
What is the subscript of U?
This is the energy density. We talk about the energy. Remember the electric energy density is 1/2 epsilon naught E squared. And The magnetic energy density is B squared over 2 mu naught.
Oh, I was asking about the subscript of U in the first one.
Oh, this one is the total.
Okay, it is just T? Okay.
Yeah, it's just the letter T. So it's the total of these two.
Okay.
And our dV is our area times our dx. Okay. So I'm going to divide by the area. Actually, let's leave it like this. Let's divide by dt. What's dx dt? The wave is traveling in the x direction. What's dx dt?
C.
C. So now, let me put this over there. The A's cancel. Oops. So then this ends up being epsilon naught, and this is electric field squared over 2 plus B squared over 2 u naught times C. But I can write this if E over B equals, C, then I can rewrite that. Remember that mu times u naught times epsilon is 1 over c squared. I can rewrite this in the following way. I can say, oh, S is equal to B squared over u naught times C by using this relationship and that relationship. But I can also write it this way. I can use the relationship again and write it as E times B times C over oops. Now, these two are perpendicular to each other. S represents the flow of energy. S is the energy in the direction of travel of the wave. And so when I define a vector that looks like this, this is going to represent the flow of energy. And this is called a pointing vector. And so this tells you the flow, really represents the flow of energy. It's some sort of flow, okay? And so if we integrate it over an area, you get a flux. So you can talk about the energy flowing out of a surface, okay? And if you do that, you get the energy flux, which is the total energy coming in or out of a surface. Does that make sense? Now the magnitude of this is the energy, is the intensity. Okay. The instantaneous value, this is where you get to see how equation driven this chapter is. Since E and B are perpendicular to each other, I mean, it's a weird dot product because theta is always 90 between the two vectors. So the instantaneous value is E times B over mu naught. And these are cosine functions. So if you take the average value, the intensity is P average over A, which is S average. Okay, so I is just S average. Which is 1/2 the maximum value, essentially. So I is C times U average. It's really, I mean, I is 1/2 the amplitude of the pointing vector. That's really for sinusoidally varying electromagnetic fields. I can be written as C times U average. Okay,
Wait.
so that's the pointing vector.
Intensity?
I'm sorry?
Oh, sorry. Does that I stand for intensity, not current?
Yes, this I stands for intensity, not current.
Okay.
Yeah, we run out of letters. Some people call it irradiance and they use a different letter, but I'll just leave it at that. So let me do an example. I got to check the time because I actually have to run to a different class. I want to write out the formulas for the electric and magnetic field to specify a wave with the following characteristics.
We cannot see the whiteboard.
Okay. I'm erasing anyway. Thanks anyway. But yeah. Thank goodness you didn't miss anything. I'm just erasing. Okay. So what are we given? We're given the frequency is 10 to the 8th hertz. The electric field is 50 volts per meter, or newtons per coulomb, however you want to write it. That's the magnitude. And the direction of travel of the wave is in the negative x direction. We're given E. Can we calculate the wavelength? Yeah, because we know C is F lambda. So lambda is F over C, C over F. 3 times 10 to the 8th. Okay, divided by 10 to the 8th. I made the numbers easy. Sig figs aren't good here, but the wavelength is 3 meters. What's omega? Omega is 2 pi times 10 to the 8th. Let's write the electric field. And you can use cosine or sine, it doesn't matter. Okay, I'll use cosine because that's what I have in my answer key. Okay, so it says that it's traveling in the negative x direction and it's perpendicular to the z direction. So it's got to be in the y direction, right? It's got to be oscillating in the y direction, right? So whether I choose plus y or minus y really doesn't matter. I really didn't specify anything. Oh, I need to write what k is. What's k? K is 2 pi over lambda, which is 6.28 over 3. I'll put a minus sign there. What about the magnetic field? Well, the magnitude of the magnetic field, how do we get that? Well, we know that E over B is C. So then the magnitude of B is E over C. And so we get 50 volts per meter divided by 3 times 10 to the 8th meters per second. And this comes out to be 1.67 times 10 to the minus 7 Tesla. And so my magnetic field, then I can write pretty easily. What do I put here then?
Z hat.
Yeah.
Or K hat, sorry.
Why did I put a minus sign here?
So that way their cross product results in the negative X direction?
Yes. What's its energy density? What is it? What is the energy density? How can we calculate the energy density? Well, there's various ways. The energy density can be calculated by this squared over mu naught. In fact, I didn't even write that down what I had with the value. But I want the average value, so the average of cosine is a half. And you should get 1.1 times 10 to the minus 8 joules per meter cubed. And then the pointing vector is that, but it wants the average pointing vector. So what do I have to do beside that? I want the average. What's the average of cosine squared?
1 over root 2.
Not 1 over root 2.
It's 1/2, sorry.
1/2, yeah. And so, I lost my place. The cross product is going to be in the minus I hat direction, right? And then I'll just get, you just plug in E and B and mu naught. I'm kind of rushing. You just plug in this value, and mu naught, and you'll get this. The cross product is going to be in the minus I hat direction.
And what are those units? Is that
It's a watt per meter squared because it's
a watt? Okay.
Yeah, because it's energy per unit time per unit area.
All right.
So I wanted to mention a lot of this stuff between now and the end of the notes is just all equation driven. There's a problem I usually do that I don't have time. Actually, I need to say one more thing. I'm sorry before I go. We need to talk about the intensity, which is the power per unit area. Think about when you drop a pebble in a pond. What happens when you drop a pebble in a pond? You get these circles that move outward, right? So what can you say about the energy in each one of those circles? Aren't they the same? Let's say if I go in a pond and I just tap up and down, deliver the same energy to every disturbance.
Then yeah, they'd be the same.
So if I had, so there's, the energy gets spread out over a larger and larger surface area, right?
Yeah.
So if I'm over here and I have an energy detector, I can't even spell energy. How much energy would I detect if the energy here is, the power here is E, the energy per unit time is P. How much energy am I going to be detecting there? Well, the energy is spread out over an area, where this is R, and then my detector has some sort of area, delta A. So this number times my delta A tells me how much energy to detect. This is called the intensity. So for a spherical wave, the intensity is P over 4 pi R squared. Okay? That picture you see there shows you different representations of the wave. You can describe a wave in terms of those circles. Those are called the wave fronts. Those are the peaks of the waves. The separation between them represents the wavelength. You can describe them in terms of rays, which you do in geometric optics in physics 215. Or you can just show them as an oscillation, a transverse disturbance. Transverse meaning that the direction of travel is perpendicular to the oscillations. Okay? So in the rest of this chapter, I'm going to ignore these. This is a question that I'd love to do, but I don't have time. If you have time to play with this, calculate the Poynting vector for a charging capacitor. You'll see that the Poynting vector points towards the center of the capacitor. That when a capacitor charges up, its energy is inward. The energy that the capacitor gets goes toward, it flows inward. Okay. In order for you to do that, to show that, you have to calculate the magnetic field in between the plates using the displacement current, and you need to know the electric field, which is pretty easy, which is charge per unit area. Okay. And then there's a few more slides on momentum, etc., which is really equation driven, which usually I don't have time to do. So you may just take a look at it, because there's a problem where you just have to plug numbers into an equation where it asks about the momentum or the force. The homework problems for this chapter are pretty straightforward. The exam problem for that you'll see on the exam is going to be pretty straightforward. Okay, you'll see an exam problem. It'll be straightforward. I always give a straightforward problem on this test, on the chapter 34 material, just because I blast through it. So if you can do the chapter 34 problem, I did put an AC circuit problem in there because I forgot to put it in the last homework assignment. But the 6 homework problems on chapter 34, there's a 7th one on AC circuit, but the 6 homework problems in chapter 34 should be pretty easy for you. If you have questions, don't hesitate to ask. Okay?
Can you just tell what was delta A on that board?
That was the area of the detector.
Okay.
Yeah. All right, so I got to run because I'm subbing for another class. So I'll be in office hours tomorrow from 4:30 to 6.
Thank you.
All right, you're welcome. We'll see you.